All right, ladies and gentlemen, this class recording has started. So, to quickly review, on Tuesday of last week, we started getting into some definitions and some basic concepts dealing with electric charge. So the first thing we talked about were positive charges and negative charges. Something that makes positive charges and negative charges similar. Actually, let's start with this. What are positive charges and what are negative charges? Where do they come from? Start there. Okay. Sarah, go ahead. Subatomic particles. Specifically, which two subatomic particles? Electrons and protons. Electrons give us which kind of charge? Negative charge, and protons give us positive charge. Okay. So, that's what positive and negative charge are. We then expanded on that a little bit and talked about objects with a positive charge or a negative charge. So what's true of an object that has a positive charge or a negative charge? What has to be true there of something that has a positive charge or a negative charge? How does something acquire a positive charge or a negative charge? Tyler, go ahead. Doesn't have the same amount of protons as it does electrons, or an imbalance of protons and electrons, which is illustrated, hold on here, right, by this picture here, right? We looked at this atom, lithium, right? Same number, that means it's neutral, but if it has more protons than electrons, it has a positive charge. If it has more electrons than protons, it has a negative charge. We talked about three ways in which an object can gain a charge. What are the three ways that we talked about that an object can gain an imbalance of protons and electrons? What are the three methods of charging? We might have only talked about two of them, but give you one of them at least. What are the ways we can do it? Some of us one. Friction, where we have two objects, two surfaces coming across each other, right? Electrons jump, okay? What else? What was the second one that we talked about? Conduction, where there's actual physical contact, okay? And then the third one that we talked about, did we get to induction? Okay, so in induction, I'm not going to go too deep into that, but let's go here to these pictures. Okay. So, for induction, here's what I want you to notice. And you have this picture on the back of your outline. Okay? In the first object, first of all, induction only happens in conductors. Okay? Because it involves those charges moving around within the conductor itself. If we look at the picture on the left, let me zoom in here for you. So if we look at the picture on the left, right, these two metal spheres, these are conducting spheres, these are two metal spheres, okay? They're touching each other, so they're basically one object, okay? But if you count the number of positive charges and the number of negative charges, what do you see within those metal spheres? What are you seeing about the number of positive charges versus the number of negative charges in these two metal spheres here? Julie, go ahead. They're the same. So technically, is this object a charged object? Technically, no. However, even though the actual number is the same, when we look at where the negatives are versus where the positives are, there is some separation there. Okay? This is induction. We brought a negatively charged object, some cylindrical rod like we were using in the lab the other day, right? We brought that negatively charged cylindrical rod over here. What do all the negative charges do? What do like charges do to each other? Like charges will repel each other, right? Same charges repel. So all these negatives, right, they move away from all these negatives. And that leaves the positives over here. Technically, they have the same number of positives and negatives, but we can get those negatives and positives to move around because of the attraction and the repulsion. Even though the total amount isn't the same, we have created a separation. That's an induction kind of idea, okay? Where we may not have an actual unbalanced number of positives and negatives, but we can separate them within an object. Like I said, a charged object, okay? Good there. Okay. Let's talk about our main business for today, and that deals with forces between charges. So, these two statements here, like charges repel, opposite charges attract. We're good with that, right? And that means that charged objects can either come closer together or they can push each other apart. But in order for that to happen, there has to be a force between them. Something to push them or pull them, depending on whether we're talking about like charges or opposite charges. That force that these charged objects feel, right, we refer to as an electrical force. So we use the abbreviation F sub E to represent the force that there is between these charged objects. How much force there is depends on a couple of different factors. We put all those factors together and we get what we call Coulomb's law. Okay? So, you guys have it written in your outline. It didn't copy over nicely here, but the force that exists between two charges depends on a couple of different factors. First, Q1 and Q2. And as you can see here, down at the bottom, okay, and you guys don't have this on your outline, might be a good idea to make some notes of this, okay? Q1 and Q2 are the value of the two charged objects that we're dealing with. Now, when we say the value of the two charged objects, we're talking about how much or how big of an imbalance is there between the number of protons and the number of electrons. If we talk about this meter stick, right, there are tons and tons and tons of atoms in this meter stick. And we said that in their natural state, same number of protons as there are electrons. Okay? If we took one electron out of this meter stick, technically it would have a positive charge because it has more protons than electrons. But is it really going to attract other things if it has one more proton than electron? Not really, all right? Those Q values tell us about how big of an imbalance is there between the number of protons and the number of electrons. If there is a big difference between the number of protons and the number of electrons, it will more strongly attract other charged things. If there's not a big difference, it really doesn't do much. Okay? The second factor is a distance factor. Right? Like it says up here on the board, D represents the distance between the charges. If we have two oppositely charged objects, they will attract each other. But if they are very, very, very far away from one another, there's not really that big of an attraction. But if they're close, there will be a much bigger attraction. Right? And that's represented by that factor D in this equation. And then the third factor, hold on. we represent with a K subscript C. And we refer to that as Coulomb's constant. It is a constant value. It doesn't change, regardless of whether we're talking about positive charges or negative charges, or lots of positive charge or lots of negative charge, does not matter. Okay? Notice, it's a pretty big number. Look, 10 to the 9th power, right? Forces between charged objects are relatively strong. How can we tell? Well, we've all done the trick where we take a balloon, rub it on our head, right? Give a charge by friction, and then we can stick it to the wall, yes, or the ceiling or something like that. We've all seen this happen before, okay? That attraction between the balloon and the ceiling in the room is stronger than all of the gravity of the whole Earth pulling down on the balloon. Yes? Right? Because if gravity was stronger than the attraction, right, what would happen to the balloon? It would fall, but it doesn't. It stays there, right? So even one balloon, with its charging by friction, can overcome or is stronger than the gravity of the entire Earth pulling on it, because it is a very big number. All right? Yeah. Good there. More importantly than what those things mean, let's talk about those relationships. This is a fraction, yes? All right? And a fraction is a division problem, all right? So, the Q values are both in the numerator, meaning if we make them bigger, right? If we make the numerator of a fraction bigger, what happens to the quote-unquote answer of that fraction? Because fraction is like a division problem, right? If we make the numerator bigger, what happens to the answer? It gets bigger too, right? If we go from 1/5 of a pi to 2/5 of a pi to 3/5 of a pi to 4/5 of a pi, right? We're making the numerator bigger. That's a bigger portion of the pie, right? So, in this case here, if we make these bigger, what happens to this? It gets bigger. What kind of relationship do we call that? Do you have a name for that one? Positive correlation, or sometimes we refer to it, more often we refer to it as a direct relationship, right? One gets bigger, the other one gets bigger. So, on your outline, Roman numeral number 4, Coulomb's law. Force is blank to the amount of charge. Force is directly related to the amount of charge. If we make the charges bigger, the force between them gets bigger. Okay? But the other factor we talked about, right, is the distance. Where is distance in that fraction? It's in the denominator, right? If we go from 1/2 to 1/3 to 1/4 to 1/5, right? The denominator is getting bigger. But what portion of the pie is that? It's a smaller and smaller portion of the pie, right? We call that a, how about an inverse relationship, okay? So force is inversely related to the distance between the objects. Direct relationship, one gets bigger, the other one gets bigger. The charges get bigger, the force gets bigger. But in this case, if the distance gets bigger, if we pull those charges farther apart, this is going to get smaller. Okay? Does that make sense? What about K sub C? What kind of relationship does that have? Okay, good. Stays the same, because what is it? It's a constant, right? The force doesn't have a relationship with K sub C because that's a constant value. It never changes. Okay? Good there. All right. So now we know about the forces that exist between these charged objects, right? Okay? And we just talked about that. That's the Roman numeral number 4, letter A and B. Okay? However, we have to talk about something else. And I'm going to put the shade up here because we need to go about this in an orderly fashion. Okay? Before we talk about electric charge, I want to talk about this. Ready? Ready for this awesome demo? Okay. Woo. It's Monday, right? All right. Why does this happen? Gravity. Okay? So, if you really think about it, okay, gravity is somewhat mysterious. In that, I'll do this, right? Billy, you ready? I'm just going to toss it to you. You can catch it, okay? All right, so I throw the ball. What happens to the ball because of my throw? It moves, goes faster, right? But when Billy catches it, right, what happens? Stops, okay? I push it, it goes faster. Billy catches it, it goes slower, right? Billy pushes it faster, I catch it, it goes slower, okay? In both of those cases, well, let's do this, okay? If I drop this, what happens to it? It falls. What happens to it as it falls? It goes faster, right? Okay? But that's a little different than when I threw it. When I threw it, I pushed it and made it go faster. But is anything pushing this when I drop it? Well, gravity, but, right? No wires, right? Okay. So that was a problem that they encountered. They're like, well, wait a second. We know that this is happening. We know it's going faster, but nothing's making it go faster. So how does it happen? Same thing when you guys did the demonstration with the water, right? The sink was on with the small stream, right? And all the demonstrations that we did basically the other day, right? If you think about it, right, you took the rabbit fur, you charged up the rod, you brought it close to the water curved towards the rod, right? Anything touching the water? No, but it happened. So what's going on? This was a problem this is a problem that people had to figure out, or they had to come up with an explanation for why it's happening. Hence we have field theory, because what do theories do? They explain stuff, okay? Back in the 1700s, a guy named Michael Faraday proposes an explanation for how this happened. And it was called field theory. Back in the day, we referred to this phenomena as, quote-unquote, action at a distance. Things are happening, but there's no contact. We are causing action at a distance. That was a problem, because it was contradictory to what we knew about making things happen up until this point. So, Michael Faraday comes up with an idea. And he refers to this idea as the force field. Okay? The force field is an area or a space. It is this space around an object where it can affect other objects. We live in the gravitational field of the Earth. Why? Because what happens when I let this ball go? It falls. It is affected by gravity. We live in the gravitational field surrounding the Earth because Earth's gravity affects objects. All objects that have gravity have a gravitational field. Okay? Depending on the size of it, blah, 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 blah. Okay? That's true of gravity, but it's also true of electrical charges. If I took the rabbit fur and the rubber cylindrical rod and charged it up over here and held it up, would the water coming out of the sink move? No. Why? Because that water isn't within the electrical field of the cylindrical rod. But if we brought it close to the water, now the water is within that field and it causes it to move. Does that make sense? Okay. Now, gravity fields are a little easier than electrical fields because what does gravity always do to stuff? Gravity always causes things to do what? Well, yes, fall, but what's happening to this object in the ground? They are getting what? Closer together. Gravity is always an attractive force. It brings things together. But we know that electrical charges aren't always like that. So what kind of field exists around these different charges? All right? Electric field, but more importantly here, is the idea of field lines. Field lines represent the electric field. Okay? Letter D underneath Roman numeral number 5 says the electric field is determined by the effect. Roman numeral 5, letter D, says the electric field is determined by the effect on a positive charge. Good there? So let's talk about these arrows. Okay? So here is, I'll use red. Red represents a positively charged object. I'll zoom in a little bit for you. Red represents a positively charged object. What do we know that positive charges will do to other positive charges? They repel. Meaning that if I take this positive charge here and bring it close to this one, it pushes away. That's the arrow that points away from this red charge. It repels other positive charges. What if I bring this charge over to here? What's going to happen? It's going to repel. It's going to push it away. That's why this arrow points away. If I bring it over to this side, what's going to happen? It's going to repel. This arrow points away. Notice all of these arrows on this picture all point away from this red positive charge. Because what does it do to other positive charges? It repels. The electric field surrounding that positive charge is represented by those arrows, all pushing away. Good there. Okay. Let's bring my positive charge over here to picture B, which is picture B at the bottom of your page as well. Now we bring it close to a negative charge. What's going to happen in this case? They're going to attract. And the arrow here is pointing towards the negative charge. If I bring it, oh, take 3. There we go. If I bring it over here, what's it going to do? It's going to attract. So the arrow points towards the negative again. If I bring it here, it's going to attract, right? All of the arrows in that picture all point towards the negative charge because that's what will happen in that case. They will attract positive charges. These arrows represent the electric field, the area that surrounds a charged object. What will it do to other things? It will push away other positives. It will attract around negatives. Okay, go ahead. Okay, so let's do this, Kate. Let's take a look at picture, or the third picture that you guys have on your sheet that looks like this. Okay? It's labeled as A, but it's from a different page in the book, not your book, but okay. So here, now we have a positive and a negative charge, right? If we threw an extra positive charge in there, okay? That's a terrible positive charge, but I'm drawing with my mouse, so there we go. It's not very good at all. So let's just get rid of that. All right. I'll go here. Okay. All right. So Kate, if I threw a positive charge in there, right? We know that extra positive charge is still going to be repelled by positives and attracted to negatives, right? So now we can see that these arrows are starting by the positive and pointing towards the negative, right? Does that make sense? Even if we moved it way over here, it would still be repelled by the positive, but eventually it would come back here. So those field lines that get cut off like right here, technically they're just kind of big circles that go around like this. Okay? So does that make sense? The arrows are always going to point away from positive charges and towards negative charges because that's how positive things will move. But if we have something like this, right? Notice all of the arrows are pointing away because regardless of where we put a positive charge in this picture, it's always going to be repelled from, because the only thing that's in that picture still are all other positive charges. Does that make sense?
Yeah, I don't know where's the between
So,
yellow lines.
okay. Technically, there are an infinite number of yellow lines. We just can't show them. Okay. So yeah, even if it's in, if it's in like this space right here, it would still be repelled. There are other yellow lines there. We just can't show them. All right. Notice, Kate, here, right? As they get closer to the positive, charge, those lines get closer together because technically there's a stronger repulsion there. And then out here, these lines are farther apart because there isn't quite as much repulsion because they're farther away. So yeah, there's technically an infinite number of lines there, right? It's just that we don't show them all, okay? But those field lines represent the field or the area. What would happen to a charge in that space? Okay? Good there. All right. It's a little bit early, but I think instead of starting in on the next outline, we should cut it off here. Quiz tomorrow will be over that outline, okay? None of the new stuff, right?
Just skip the induction.
Oh, induction, right. So, with induction, I kind of went over it quick at the beginning today. Really, we're talking there, when you have induction, you have a separation of the charges. Let me do this. Let's go back to that picture so we can reference it again. Give me one more second here, just finish this up. Alright, so in this, right, we talked about here, technically those charges are separated. Positives over here, negatives over here, but if you count the actual number, there's the same number, right? So technically, this object is not charged because it has the same number of positives and negatives, but we can get them to sort of separate out based on what's surrounding it, okay? So inductors only happen in conductors because we get that charge to move around. Technically, we've separated the charges without imbalancing them. Does that make sense? That's, if you get that about induction, you'll be good to go. Okay. All right, good there? All right, let's chop it off there, or cut it off there for today. Quiz over that outline tomorrow. Then we'll get into voltage and current and fun things like that.